Awesome. All right, so first of all, these were the old quizzes, but so they're no longer for credit, but we're going to continue using them for the partial credit or the extra credit. So anyone want to try to give this one an answer?
Yeah, it's B.
Very good. So yeah, F1 score is the harmonic mean of the precision and the recall. Who said that, by the way?
Karthik, Kartik.
Got it. Note it down real quick. All right.
Max, there were some answers also in the meeting chat window.
Oh, were there? Oh, there was some there. Okay. I'll go back and look at those at the end. I want to stay in the presentation thing there. Yeah, generally, if you want to do an answer, try to do it with the microphone just so I can see you, because otherwise I don't have it up on the side there with MS Teams. So, again, logistics today, we're going to be talking about the homework assignment that will be released tonight. Actually, it's already been released. Also, we are releasing the lab, though it's kind of a soft release because there's still you still have a bit of time to actually get started on that. But if you want to get started early, this is probably the time. And today we are finally talking about neural networks. So first things first, here we have some terms. I'm just going to gloss over these mostly because it's just things to look back on. We'll get into the specifics later. But the important ones are an ANN. If I ever say that, it's just shorthand for artificial neural net. A neuron is a single unit of a neural net. And we'll talk about those in quite a lot of detail in a moment here. Epoch is going to be one forward pass and one backward pass of every training example. So this is during training. This is going to be one full go through of your training set. And we'll talk about activation functions more later. We'll talk about loss functions more later. Backpropagation is this algorithm we use that we're going to talk about today. That we use to apply gradient descent to every layer of a network. If you didn't understand any of those words, again, it's fine. These are what you're going to be learning today mostly. So, getting kind of a baseline here. The important thing to note about neural networks: they are not the digital version of biological neurons, as I'm sure you know. They're also not really based on biological neurons. That would be too strong of a relationship to give them. Really, ANNs are inspired by biological neurons, and that's about where it ends. There are certainly similarities, but it's not really fair to compare the two because biological neurons are incredibly more sophisticated. They have a lot more, we can call it computational power, I guess, but a lot more functionality involved in them. This is a pale comparison, really, but it's worth noting that that is the inspiration they come from. And as I say, don't compare these too much. On the very next slide, let's compare these too much. So, can anyone tell me, can anyone point out any specific structures on this neuron, this biological neuron?
There's the myelin sheath.
Yep.
Right there in the center.
Yep.
I think the branching parts are also called axons.
Not
or am
quite.
I wrong about that? No. Axon. No, that's wrong too.
That's correct, but not for all the little ones. Axon is this big boy here, the long one.
Are those dendrons?
Dendrites.
Dendrites.
Dendrites, yes. Very good.
Okay.
What's this?
The nucleus.
Yep, and the cell body, but in the nucleus, in the cell body is the nucleus. But the important things we're looking at here are definitely these. We have our dendrites, our nucleus, and our axon, and that's what we're going to see as being our inspiration of our structure. So let's talk a little bit actually before we go on about how these work. Information comes in here through electrochemical exchanges in the synapses. That information flows through into the cell body, and then you can almost say is computed upon. Not necessarily much computation, but sometimes it can be a lot in the cell body and in the axon, and then it is finally outputted at the end. So it's this very small unit of computation in which we have these multiple inputs. We have them feed into this single area in the middle, and then we have one output. So that's the structure we're working with here. It's also notable that in a case where we have brains and such, such as our humans, or if you want to go something smaller than brains, you can go like the small neural clusters that certain bugs will have. You basically just have huge networks of these neurons that are all strung together and connected in different ways, and they form a mesh of cognition, we can almost call it. It's just these this huge, elaborate computation pattern. Another thing probably to note, I probably shouldn't get too detailed here, but an interesting thing with these, the strength of one particular area of computation, one particular pattern that we're going to be seeing within these neurons, depends on how close the dendrites and on the axon are to the dendrites in the other neuron cell body. So if we have right here, it looks like this is a dendrite from a different axon, from an axon of a different neuron connecting to this neuron. Depending on how close those two are, how almost touching they are, that's going to determine how strong that pattern is. So yeah, and again, we can see this information flow we have going from the left side, where we have our dendrites, all across the network. Now, here is our artificial neuron. In this case, we have a bunch of inputs. We can think of these like our dendrites. And each of them has a weight. We have x1 through xn, and they have w1 through wn for this neuron J. And that is very interesting because it kind of models what we were talking about with the closeness of the dendrites. So these weights are going to symbolize the importance that that particular input has on this neuron. Then we sum those. We apply an activation function, and we get an output. Now, that glosses over a lot, but before we get too much into that, let's talk about this right here, this little term. Does anyone have any guess as to what this term is called? If you've taken other ML classes, you might know.
The bias.
Yes. Who is that?
Nicholas Rose.
Nice. All right. So yeah, that's the bias. That is going to be, you can think of it as being a number that in itself is just going to be added in to the sum, and that is a learned parameter, but really the best way to think about it is an input that is always 1. It still has a weight, like we see here. In this case, we called it theta, but it is a constant one size input with a weight that can be learned. And we'll see about why that's important in a moment. This activation function too, we're going to get into in a second, but for right now, just know we have this function, and the entire structure of this is inputs, weights, sum, with the bias, and then function, call, all of that. Here's a bit of a more list form of what we just talked about. So we have our inputs, weights. Sometimes we have a bias. We don't always actually have a bias. You can train neural networks without one, but most cases you will have one because it's almost always useful. We have an activation function. This is sometimes called AX, sometimes it's called alpha X, sometimes it's just f of x. I will probably be using f of x or a of x at most points. And we have our output. Now, this is the formula, the algorithm, the Krabby Patty secret formula here for running our forward pass. We multiply our inputs by the weights. So we take every single one of these x's and multiply it by its corresponding w. We sum those, we sum all of those together. We take that sum and put it into our function as an input. And the output of that is the output of our neuron. So that is the entire forward pass. And if you're confused why that helps us, that's totally fine. We'll get to that in a moment. But just know that that is our algorithm here. Multiply inputs by weights, sum, activate. So we're going to start with the most kind of mysterious part of this, because I remember when I was first starting to learn about neural nets, I kind of was, I was trying to figure out where the magic is. Where's the part that makes it happen? And I was kind of thinking, oh, maybe it's this activation function thing. It isn't, and I want to make that clear just by showing in detail what it is first. Activation functions, the entire idea of these, is really just to restrict our output, to change our output into a specific format, and map it onto a range that we want for whatever task we're doing. A few examples here. We have Sigmoid. This is used a lot, so what will happen is the weights are multiplied, the inputs are multiplied by the weights and then summed, and then that value is put in as x here. And we'll get somewhere in this range. Can anyone take a guess as to why this sigmoid function is a useful activation function for some tasks?
Is it because all the output is between -1 and 1?
It's between 0 and 1, actually, with this one. But yes, that is absolutely the
For
reason.
classification.
What?
Maybe for classification, since it maps like to 0 and 1, that might be useful.
Yeah, exactly. Both of those are correct. Can I get both of your names?
Mingzhu Li.
Gotcha.
Thank you.
And Honor, O-N-U-R.
Very good. All right, well, yeah, that's absolutely correct. We have, this is mapping, sigmoid is nice because it maps our input between 0 and 1. And it has this nice gentle curve. You'll notice, and we'll learn why this is later, we want to try to avoid most functions that don't have a nice gentle curve like this. We want it to be something that's very easy to do derivatives on. So here's another one, Tanh. This, you can see, is very similar to sigmoid, except that instead of between 0 and 1, it's between -1 and 1. So if that's the range you're looking for, or maybe a multiple of that, maybe you want it between -3 and 3, you do 3 Tanh. But these are how you can map these ranges out. Here's another one, and this one is not as pretty as the others, but it's super, super, super useful, and we'll use it endlessly in the future. This is ReLU. It is an extremely simple activation. It is just the maximum of 0 and x. So if it's a positive value, it's going to be just as it is. But if it's 0, it's going to be 0. Or if it's less than 0, it's going to be 0. It cuts off the entire negative tail of that. And I'm not going to get too much into why that's useful just yet, because that's a whole different thing, but it's good to know that it exists. If you want a version of that that's a little bit nicer and isn't as honestly isn't always as useful, sometimes it's as useful, but it's definitely follows that gradient a little better. We have ELU, which is it's the same thing, but we've kind of tacked on this tail. We have an alpha value that we can just set to be whatever we want, basically. I use 0.5 here. But it gives us this tail so that it's more of a continuous function. We don't have some like weird little blip in there. So we talked about, we looked at neurons already, though. We looked at this structure as a graphical representation way back here. We saw this little graphical representation of our algorithm, but that's not the only way to look at it. In fact, we'll be looking at it in several different ways in this course. But another useful way to look at it is as a function, as a mathematical function. So in this case, our neuron, which we're going to call f of x1 through n, for however many inputs it has, is going to equal our activation of our sum of our x's multiplied by our w's plus b. That's our bias term. So, and technically, this is very slightly wrong. I did a goof here. Can anybody tell me what the goof is? Has to do with this general area.
Is it okay for the bias to be in the summation?
Exactly. In that case, we're just adding the bias every single time, and that's not what we're really going for here. Really, this is closer to being plus b on the outside of the sum. Who is that?
Me, Shubham.
Gotcha. Cool. So, yeah, we have our function here. We have our activation, our sum. This is the same thing we were looking at in that graphical representation, except this time it's as this mathematical function. So, what we want our neuron to do, though, is we want it to learn to do something. We want it to act in a certain way. We want the function that we made there to mimic another function. That's what learning really is. It's mimicking another underlying function. And that might be something very simple. Like you could have a neural net that learns how to do certain math equations or something. And in that case, it's just actually training it on that function. But it could also be something more implicit, something like the function that classifies images or something. Anything really that you want to put in a function. And we want to do that by only changing the weights of the neuron. We aren't going to change the activation ever. We're always going to do our sum and our multiplication and everything, only the weights, including the bias weight. So what we're really trying to do is to find a set of weights that makes our neuron function act like some other function. How do we do that? Well, I'm going to tell you, It's a super dark secret that's been kept since the beginning of time. It's the government doesn't want you to know. It's some real Illuminati type things here. I'll reveal it to you though. It's this magic wand. This is the magic wand right here, and it's very special. If we thoroughly poke our neural network with it, it will change the weights to something that we want. You might not believe me, but just wait and see. We'll see how this beautiful instrument works. So let's do that. Here I have a neuron. It has a weird activation function that we almost never actually use, but for this case, why not? It's just this piecewise between 0 and 1 kind of thing, right? Makes sense? So this neuron here, it can either output 0 or 1. And that's good for us, I guess. Let's make it do stuff. In this case, let's make it do Nand. This is going to be our function. We were talking about neurons mimicking a function. This is that function. So in this case, we have our x1 is 0. If we have both zeros, then our Nand is going to end up being 1, right? In fact, Nand is going to be 1 in the except when it's both values are 1, because Nand is just not and. So if we set our weights to be -2 and -2 and 3, that'll give us this kind of truth table here of answers. And once we have that in place, we're good to go. Like you can see, this is a correct neural network. This will every single time act like a Nand function. Does everyone understand that idea?
I'm having trouble grasping like exactly how it gets to mimicking a NAND function.
We poked it with the magic wand.
Okay.
Well, don't worry about it. We'll talk more about the magic wand later. But for right now, we poked it with the magic wand to get it here. But you understand how it got to this, or how it operates now that it's in this state?
Yeah.
Cool. So yeah, and we can go through a quick example. Like we could do 1 and 0, 1, -2, 0, 0. So we end up with -2 plus, in this case, our bias, 3. We have a value of 1 that goes through our activation, becomes 1. And in the same way, you could do this with the 1. So you could do -2 and -2, add 3, that's -1, and that becomes 0. Because, again, this. Can also do NOR. You see, the only thing that really changed here is instead of having our weight for our bias be 3, we set it to 1. And it goes through this calculation just fine here. It is perfectly mimicking this function now, just as it was the NAND function. So we can create all these different structures just by changing the weights. You can think of that single neuron as being a very simple but fairly effective function mimic. And once we have our gates figured out, once we have our Nand and our NOR, we have all computation right there. That's all of computation, universal logic gates, so you can make anything out of those. So there you go. There's all computation figured out as neural nets. But we can also do something a little more obviously useful. In this case, we have this little classifier. It's a super weak little one. and we have our inputs being these binary inputs of 1 or 0. Is the company named Enron? That's not going to go so well. Is the company in debt? That's going to be negative points. Is the company an experienced CEO? That might help them. If they have investors, that might help them. And all of this is going to help us determine whether that company will succeed or not. Also note, this particular classifier is not very good because it seems to be overfit. Anyone want to risk a quick guess as to what overfit means?
Does
So
it have-
overfitting means like when the model is trained, like when the function is trained to like just work on the training model itself, and like when you hit it with some other training data and it like performs like not in a correct way.
Yeah. So in this case, it was apparently trained on a company or a database with Enron in it, and it realized that Enron exploded. So it heavily punished being Enron. But in fact, you could have a company that isn't Enron but happens to be called Enron. They bought the name or something, but they're in farming supplies instead of energy and such. I don't remember exactly what Enron was to do with. I know energy was involved, but I think it was a little more financial. I don't remember. Anyways, just as we can have these networks of neurons, we can also have networks of artificial neurons. Actually, before we go on, does everyone understand this pretty well? The idea of using this as a classifier? All right, that should be good. So here's our structure. In this case, we have our inputs. Every input is going to go to every neuron of the input layer. In fact, what you should really think of these as, these starting neurons, is not even neurons just being the inputs, but we have our inputs. Each input goes to every single neuron once. So in this input's going to go here, 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 and here. And then this neuron is going to do its computation. It's going to do its multiplying its weights. It's going to do its summing. And finally, it's going to output one single value. And that value is going to go to every other neuron in the next layer. And so on until we have our output layer right over here. So this is it. This is our neural network. Here's one of them. Here's another one of them that I had to edit slightly. So in this particular case, anyone want to try to real quick run through the calculation and figure out what the output's going to be? You can use paper or anything too. It might take a second, but.
Is it 116?
Probably. I didn't actually do it.
I just did in my head. I didn't double check it.
Yeah, it sounds about right. So we can go through part of it together actually, because that might be good because it includes our ReLUs here. So we have. Let's start with just this side. So we have 10 goes into 2, so we have 20. 3 goes into 3, so 9. That gets sum to be 29. ReLU, it's still positive, so that's fine. 29 times 4, I'm not going to do that in my head. And then we finally, whatever that answer is, that 29 times 4 is in fact going to be summed with the other side. So that's going to sit here. On this side, though, it's a little different. We have our 10 go in, so we have negative 10. Or a 3 go in, so we have 3. 3 plus negative 10, that's negative 7. But we have our ReLU here. So ReLU is going to make that whole thing 0 because it's negative. Then that 0 gets passed on. 0 times negative 2 is still 0. So we, again, just end up with our 29 times 4, or whatever that is.
The 116.
16. Awesome. Good stuff. So yeah, that's the answer. We did it. Who said that answer first?
Joshua.
Cool. A lot of extra points today. Good stuff. Just by the shape of this is kind of a weird question, but what is this? I'm not showing you the weights. I'm not showing you anything else. Just look at the shape real quick and try to understand. Try to give me a guess as to what this is.
Looks like an adder.
Very good. That's probably the quickest I've had someone get it in this class. Yeah, this is an adder. And again, this is not how a normal neural net's laid out. Usually we have it almost always following this structure. But I like this example because it's important to know here that neural nets, you can use them creatively. You can use them in these weird ways, and you could still get really good results out of them that way. One of our projects we're going to do is based on a paper that was just using a neural net in a really non-standard way to get an output that we wanted. You can be kind of hacky and creative with these, and it can give you some really cool results. But to move on, here's another kind of picture here. Now what I've circled here are blue boxes, including the ones that are attached to the biases, these weights. This is the only information of the network. Everything else is architecture. So if we are saving our network, storing it, changing it, this is all we're worried about. Everything else is going to stay static throughout the life of the network. With asterisk, there's some exceptions when you get to more advanced versions of this, but generally for the most simple versions of these, it's going to look like this. And let's not forget, though, these neurons were functions. We were saying before that this f of x1, x2, x3, x4, etc. equals the activation of the sum of the x's times the weights plus the bias at the end. And in that same way, these neural networks are also functions, but instead they are functions of functions. So in this case, let's look at our F3 here. The output of this network, this entire network, is going to be F3 of F1 and F2 of the input. So if you wanted to build it up the other way, X1 and X2 get put into this F1 function. X1 and X2 also get put into this F2 function. And then both of those outputs are fed into our F3 function. So we can look at that. And that was a good functional perspective. That was a good structural way of looking at it. But it's all to kind of hammer home this idea that a neuron or a neural network is just a very, very general function. Depending on the weights involved, the values of those weights, and how complex your network is, how many layers and neurons you have, it can mimic other functions, and sometimes very well. You can make it a classifier that's classifying images. You can make it a regressor that's trying to predict stock prices. You can have it be a clusterer that's doing some sort of clustering tasks to understand maybe doing anomaly detection. That's one thing I'm working on recently. It can generate. You can have a function that's generating new images from random noise. You can do pretty much anything with these. If you can put it in the form of a function, if you can think of it that way, in this input-output sort of idea, you can try to make a neural network do it. Will it work? Maybe, maybe not. But you can certainly try, and then you're going to hit it with the magic wand, and it's going to give you your weights. But I should probably get a little more into this magic wand. I haven't given you all the secrets yet, all the dark secrets of the magic wand. You've actually, despite the government trying to keep me from this, despite the CIA have been at my door, despite all of that, you've already heard of the magic wand before. You've, in fact, been forced to hear about it, and you probably were. I don't know. Some people in CS like that class, but I don't. It was tough. The magic wand is calculus, and it does exactly what I was saying that it does. I was not lying about the magic wand, and anyone who says I was is just the most libelous of people. So first, before we get into that calculus in detail, though, let's talk about these loss functions. So we are going to give our network a loss function. This is basically going to tell us how badly our network did. So if we have a true value y, we were talking about x and y in classifying. If we have a true value of y, and that could be our class label or whatever, and we have an output value of y hat, that's going to be whatever our network outputs. The loss function is going to tell us the difference between those two, or the error between those two, sometimes in somewhat roundabout looking ways, but often important ways. You can also, it's not doing the flat mathematical difference. It's not just doing y minus y hat most of the time. Sometimes it is. But the basic idea here is we're taking these outputs and we're seeing how poorly they performed. We're seeing how far from the real output they were. Sometimes it's called the cost function or the error function. Usually I'll just call it the loss function, but those terms are in use as well. We're going to look closer into those at a different lecture, but here's a few that exist. The big ones you'll be working with ever are like cross entropy, binary cross entropy, and like mean square. MSE is really heavily used. But anyways, to state the problem more precisely, we have to find of learning these neural nets. We need to find a set of weights for each neuron that minimizes the loss. So we want to get the loss function to be as small as possible by changing the weights. Well, let's look back to our good old friend calculus. We can find the direction of decrease for a function by finding the derivative. In this case, we have this nice, easy to see 2D function, and we have we want to find the smallest point. We want to get down here if we can. So by finding the derivative in respect to each weight, we can find how we need to change that weight to make that loss function go down. This strategy is called gradient descent. By using it, we can minimize the error in our network due to our weights. And what that will result in is, again, this nice general function that is able to mimic a specific function that we've trained that on. So let's also talk about learning rates real quick. This is one of those subjects that could be its own lecture if we wanted to expand it, but we're not going to. The basic idea, though, is we have this nice little value eta here, and we're going to make it a very small number usually, and and then we're going to multiply it by whatever adjustment we're making to our weights. This is just to control how fine-grained our movements are for this neural network. And we can get a little bit farther into what I mean by that in a bit, but the basic idea is we don't want our weights to be changing a very large amount all the time. We want small, little micro adjustments to our weights. This makes sense how we would do this for just one neuron, right? Because we have our very simple function where we have our activation, we have our sum, our multiply. We can do a gradient to that. We can find the derivative of that with respect to weights very easily. However, we can't really do that for a neural network where we have all these neurons together. So we need to generalize this to multiple layers. We need to have our outputs. We need to change the weights of our whole neural network such that the output is changed in a positive way, making our loss function smaller. And we have to divide up that adjustment across all of the different sub-functions of our neural network function. Well, we can look at that again this way. So our loss that we're getting at the end here is going to be our loss function of our activation of our final output, which is in fact itself we can take that layer output I. That is a function of an activation of a previous weight and a previous output, and it'll go all the way back through the network. So this is a really long function that we have to keep expanding as we go deeper into it. And we're basically trying to find the gradient of that. So the question is, how do you find the gradients of nested functions? Anyone have any idea?
Do we use the chain rule?
Very good. And that was Colin, right?
Yep.
Cool. Yes, we use the chain rule. And here's that. So we have, in this case, we are looking for our change of L loss with respect to W weight, or delta L over delta W. So we can have this function in a chain rule. A reminder for that was we have a function f where we are taking f of g, and we have g which is taking g of x, and x is our input. In this case, we're doing delta f, delta x, so with respect to x, and we are doing our chain rule to do that nice little canceling across thing to get our delta f, delta x. And that's exactly what we're going to be doing here. We're going to be using the chain rule across every single layer of our network. Yeah, I think this mostly just says what I said before. But again, just going back to the functions thing, we're trying to mimic our I/O patterns by changing this loss. This big picture view, I hope you all understand that, and why I'm hammering it home so much is we're trying to change these weights to minimize our loss function, which is also hopefully making our neural network mimic these input-output patterns of a function. So quick little example thing here. We have this neural network. It has two inputs, x1 and x2. It has an output y1 and 3 hidden neurons. It doesn't actually have 3 hidden layers, it just has one. I miswrote that. 1 hidden layer, but 3 neurons in that hidden layer. And there are 6 weights here between our inputs and our hidden layer, and another 3 weights going from our hidden layer to our output. For loss, we're going to be using this MSE, mean square error. That's what this looks like. And we're going to be using as activation, we're just going to be calling it f of x. And we're going to be calling the derivative of that f prime of x. So here's our 2 weights as these nice little matrices. Now, assume also we're given our L1 output. We've done a forward pass. We have our output from layer 1. We have our output from layer 2. We have the loss that we've been talking about. We have our f prime of f prime, which is our activation derivative. And we still have our input and output. We still have our x and our y, our expected output. First thing we need to do is get the error for this final piece here. In this case, that's going to be the loss of, or the derivative of the loss between y and L2 output, which in this case is just going to be y minus L2 out, because derivative, so we can, that 2 goes down here, and it just becomes y minus y. Next, we're going to get the delta, the change of that particular layer. And we're going to do that by multiplying this L2E we just got by our f prime L2 out. Next, we need to get our layer 1 error. So this is going to be our error for this layer here. For that, it's going to be our layer 2 delta that we had before, dot product with the transpose of the W2 matrix, weight matrix. Again, we can go backward one more step and get our layer 1 delta by, again, doing the same thing, taking our layer 1 error and putting in the derivative activation of the layer 1 output. So we've done all of that. Now we can get our adjustments by taking the inputs from each of those layers. In this case, we have our transpose of x, so that's going to be this. And we're going to dot product that with our L1 delta. And for our layer 2 adjustment, same thing, except the input of that was L1's output, so we can put that in there. And dot product by L2 delta. And for both of these, we're multiplying by our learning rate. So that might be a bit confusing, but I highly suggest, especially before you get to the homework or the lab, just going through this. This is basically the formula you're going to be following for making your own backprop. These are the main values that we're calculating and how to calculate them. And if you want to look at this, a slightly bigger picture look at it, when we do our learning, when we're doing any sort of neural network learning, we're going to run a forward pass, returning the output of each layer. We're going to calculate the loss of the last layer's output and versus the expected output. We're going to calculate the last layer's delta value and of its loss and the derivative of the activation function. We're going to calculate the error and delta of the previous layer before that using the chain rule, and we're going to continue doing that until we get to the last layer, or in this case, the first layer. Remember, this is back propagation, so we're going from this side to this side. And once we have all of those delta values calculated, we can get our adjustments, and we can add it. Just all we have to do is add those adjustments to the weights, and we can continue from 1 and do that over and over again for many different epochs, and that will train our network. That is the poking it with the magic wand. I'm not going to play this video because it's over online, but I have this video embedded here because it's really good at explaining this in a little more of a step-by-step way. So I highly suggest when you're done with this lecture, go ahead and take a look at this video, give it a watch through. And that's about it for the actual lesson today. Real quick before I move on to the homework, are there any questions still about that backprop? If you're confused at first, don't worry, just read through it a few times mostly. It's a tough thing to understand, but it's important, and once you get it, it's in there a lot more.
So is the reason that that we want a smooth function for the activation function that way we're actually able to take a derivative of it?
Exactly. That is exactly that reason. So the reason why we want like sigmoid to be a nice smooth function instead of being something like we had in our logic gates one is that sigmoid is very easy to derive along all points, which is what we'll be doing. We're doing that derivative operation. So yeah.
Awesome.
Any other questions?
So what exactly is delta?
Backpropagation is the algorithm that we're using to learn the weights for our network. So that is this. This entire thing here is backpropagation. It's this idea of starting at the end of our network, getting the error and the derivative there, or the error and the delta there, using the chain rule to then get the error and delta of this layer, and doing that over and over again so we can get these adjustments. The goal is to get these adjustment values so that we can change our weights and improve our neural net.
Just to, can you clarify like what exactly the delta and adjustment mean for, like why are we looking for it? Error, I understand it, but delta and adjustment, I'm a little bit confused.
Yeah. So the delta is, you can think of the delta as just being applying our derivative function, because this is just, we're just doing derivatives here basically, to our activation. Delta is going to be the overall change of that layer that will accomplish lowering our loss function. It's how we need to change the layer to make our loss function better.
So basically slope, something like slope.
Sort of, yeah. You can think of it that way almost. Okay. And then adjustment is this actual value we're calculating when we take into account our input for it. So we're doing our dot product of that with the delta. And what that's going to be is a matrix that's going to be the same dimensions as our weights. So we're going to have an adjustment and a weight. And it's going to go through, and well, actually it won't be a matrix. It's just going to be one value because dot product. But it's going to go through and add that to the weights and changing the weights. Does that make sense?
I'll try to understand it by looking at it.
Okay, yeah, give it a couple more read-throughs, but if you still keep having problems with it, we can schedule help hours or something. I have 252 help hours, so we can always jump into those too.
Okay, Max, I will have to go now. Okay,
oh, that's okay.
Thank you very much.
Yep, see you later, Gustavo.
Okay, bye.
Bye-bye. To finish this up, though, let's talk about the homework real quick. We are going to, this homework here, it's basically going to be a step-by-step run-through of one feed forward and one back propagation of a network that we give you. Just take it step by step. You don't need to show the calculus, just show the basic operations. Basically, follow this. Do all of this for that homework, just written out by hand, or on a computer, however you want to do it. And that's about it for that. I'm going to show you that as well in a minute. Some links, so just looking at those, especially if you're having confusion, this is probably all these videos are a good place to look.
The slides are on the website, if I remember correctly.
Yes.
Okay.
Yeah.
Just wanted to double check.
Yeah. And yeah, here's the website again. So the slides are all, we have our slides, we have our videos that are these lectures, we have our watch before lectures, all that. Here's that homework though. So in this case, we have this very simple neural net. I've given you some information about it. I've told you we're using MSE. And basically all we're having you do here is with these inputs here. So these are our weights. These are the weights that we're starting with. You're going to have to go ahead and run one forward pass and one backward pass over this network and fill in these little boxes here and try to show your work as best you can. Doesn't need to include the calculus. And that's about it for the homework. That won't be too bad. I think I set it to be due 9/9, so next week. Lab 1 classification, that one is going to be due in about 2 weeks, a little over 2 weeks. I might extend that, but probably going to keep it as it is for the moment. Lab 1 is a little more complicated. The best way to know about that is to just read the handout here. It's fairly in-depth as to what you need to do. But I probably wouldn't get started on that. I would give it a read over, and I would look at the skeleton code, and I would make sure that your environment is set up so you can like run the skeleton code without having errors before next lecture. But then once you get to, I probably wouldn't try to get too deep into it until next lecture, unless you want to, look ahead a bit. But that's it for today. Any final questions, thoughts, concerns?
If I remember correctly, we're going to be using the same project throughout the semester, right? The same code? Or
no, we're going to be using 3 different ones. So we have,
okay.
Yeah, we're going to be using the same like format for it, but we're going to be using different skeleton codes.
Okay, makes sense.
Anything else?
Do we have to learn TensorFlow for the lab, or would that be covered in the lecture as well?
We will have, our next lecture is actually going to be on TensorFlow and just generally implementing these neural networks. This was kind of the theory part, and next we're going to be doing the implementation part. So yeah, you can wait for next class for that, but if you want to get started on that, that's definitely fine. We're mostly going to be using Keras, which is kind of a high-level library built on top of TensorFlow, as well as other neural net libraries, but yeah.
Thank you.
No problem. So let me, real quick, before we go off here, check the chat, see if I missed anything there. No, that was some answers there. All right. So I think we're good then. Sorry we went a little bit over today, a half hour over. I marked this class off as being 2 hours a week, and then we usually will just do 1 hour a week. But this lecture takes a while, and that should be it for today. Thank you, and I will see you next week.